Okay, so this is an introductory video to use block RAMs in your RTL. There are multiple ways to do that, but I prefer using this specific way. I'll just cover it. So what I do is that I use language templates. If you're using Xilinx ISC, language templates are this icon. If I click it, so this window will open. So it won't be open by default. It was open already here. So here you can go to Verilog, and then you can go to synthesis constructs, and then you can go to coding examples, and then you can go to RAM section and use block RAMs. So there are multiple ways you can use block RAM. The most general way is to use two clocks and two read and write ports, but I'm covering the simpler way, so you can apply whatever you learn here on this as well. So but I'm using covering the simpler one, that single port read and write block RAM. So here is an example code for that. So how to use this code is that you replace all these angle brackets things with whatever variable names that you prefer. So you can make a reg or var. This will be an array, and you can use it. So what we can copy this code and make maybe a new file and paste it here and save it as a bram.p or something, and or copy this code inside our code somewhere. What I personally prefer is that I create a module out of it, so that whenever I require to use it, I can just instantiate that module. So this is what I have done already. So I'll just open that file instead. So this is the bram.v file that I've created out of this code. I've replaced all the names in the angle brackets with the variable names, and I've made the control signals like RAM enable, write enable, address, data in and data out as input and output ports of this module. And another thing that I've done is that I've created these parameters that can be used to customize this block RAM whichever way I like. So at the moment, just focus on the first one. So there are two variables, RAM width and RAM address width. So RAM width defines the data width of the RAM, that each value will have this width. So I just want to use 32 by 512 RAM in this case. This will be one block RAM in most of FPGAs. In newer FPGAs, it could use half of a block RAM, but in most FPGAs, this is one block RAM. So one block RAM is generally 32-bit wide and 512 deep, or you can configure it to be 16-bit wide and 1024 deep, and you can keep halving those to single bit. So you can change the width from 1, 2, 4, 8, 16, and 32. So in this specific case, you can change it to any value. So if there is an in-between value, it will just use the block RAM, and some of the bits will be wasted, which has to be done anyway. So RAM address bit is basically how many address bits are required. So if it's a 512-bit RAM, 512 deep RAMs, that means there are 512 locations in the RAM, then I have to have 9 bits of address. You can take a log base 2 of the number of locations that you want in your block RAM. So log base 2 of 512 is 9. So this basically means that my address will be 9 bits. So address will go from 0 to, if we have all ones in 9 bit, it will be 511. So total address will be from 0 to 511, which means that there will be total 512 locations. So this is the block RAM that I've used. And here's the test bench. So in the test bench, I've just initialized block RAM with some values. So here I've instantiated the block RAM, and this way I can give the parameters. At the moment, I've used the same parameters that I've used 32-bit wide and 9 bits for address, that means 512 deep block RAM, and I've used the same file name for data file.txt, but I won't be using it in this example. I'll be coming to this later on. So here in the test bench, I've written a loop that increases address from 0 to 20 and writes data 10 times the address. So on 0 address, 0 will be written. On 1 address, 10 should be written, and for 20 address, 200 should be written. So Then I have written a reading loop where I just deassert write enable. So here I have deassert write enable, and then I just cycle through the addresses 20 times and then read back whatever value I get. So this is my test bench. So if the values have been written correctly, then I should read back 10, 0, 10, 20, 30, and so on. So here we'll go through that. So I'll just compile this code. So this code is in the same folder. Here's the folder. No, it's not the folder. Here's the folder. Let me see. So here's the folder where I'm writing this code. So this is the bram.v file and this is the tbbram.v file. So I'm just compiling these files and I want the output to be VRAM. I'm using Verilog to compile it, but you can use any simulator that you want. So that's another use of using this code, that you can make it simulator independent. You can use whatever simulator you want. You can use Verilog, Model Sim, Xilinx ISC, or even Quartus. You can use anything you want. So it should run. So now you can see that on address 0 we have data 0, on address 1 we have 10, and so on up to 190. So the next case is that we want to initialize it with the block with a data file. So I have created this data file that has values from 400 to incrementing by 4 up to any value. So that doesn't matter. So now I'll come back to the parameters. So if you look into the code, there is an initial statement. This normally initial statements do not synthesize, but in this case it does. In this case, what it does is that it initializes the block RAM with whatever file that we have given. So in most FPGAs, we have this option that we can give a we can initialize our registers or block RAMs with values. So this initial statement will do that. So I have created a parameter for file name, whatever file name we want. Then I have created two parameters, start address and end address, which are 0 to 10. So I just want to initialize from data file.txt, but I just want to initialize from 0 to 10. So it is starting from, in number is starting from 1, so we should go probably up to 11. So we will have up to 428 values in the block RAM, and we won't have any other values after that. So so that's the way we use these parameters. So in this is start address, end address, and data file. So I've given the same values in I haven't given any value to start address and end address here. So that means if we don't give any value, then the values in the original RTL, this file, these will be considered the default values. So if I don't specify a value, the parameters values here will be chosen. But if I specify here something, then this will be overridden. So whatever I'll specify while instantiating will be used instead. So these three values will be initialized, but rest of the values, that is start address and end address, won't change. So if I copy paste here and I change them, then I'll be able to change them. So in this case, I don't want to write something into the block RAM. I just want to read it to verify whether whatever I have written has been actually written on the block RAM or not. So I'll recompile it. I'll just quickly go through it. Let's recompile this. I'll run it. So you see that these are decimal values. So I just want to print them in hex because I have written values in hex. So I will use %h in $display. That means that we want it in hex. So I'll just clear the screen, recompile it, and rerun it. So here you can see that we get values from 400 to 428, the first 0 to 10 values, and rest of the values are not initialized. So if I change it, maybe I want to initialize some more values, so I can maybe copy paste from here to test bench the parameters, and I can change the values, maybe. So dot, and I don't want to initialize till 10 values. I want to initialize till, let's say, 15 values instead. So insert comma here and a comma here. So instead of 10, I want to use 15. So let's say I'll do that. So if I now compile it again and run it again, now you can see that we have 5 more values here, so that are used for initialize. Similar way, if I want to use a different file, I've created another file, data file 2.txt, that instead of 400 starts with 4 to C. If I just change the file name from data file to data file 2. So now instead of data file, which was the default value or given here, it will be overridden by this value. So now I should clear the screen. So CLS, and I'll just recompile and rerun it. So now you can see that it starts from 4 to C instead. So what I like about this specific way to use block RAMs is that once I have made this module, I can reuse it whenever I want to instantiate a block RAM. Otherwise, if I just need one block RAM, I generally prefer the other way, which is using device primitive instantiation. So here I just need to just instantiate a block RAM instance. It's just the instance. I don't need to write any code. Just copy paste this code and just tie specific ports. This also works, but this will only instantiate one block RAM. So normally we want to have this option that instead of just one block RAM, I want to have a bigger block RAM. So if I want to have a block RAM that is as big as 16 block RAMs of in an FPGA, I can just change this RAM address bit. I can increase 4 bits here, so it will be increased. So it's very flexible. So so I don't need to use code generator or anything that is the tool specific thing, and I can reuse it again. Similarly, if I want to port it on some other FPGA, for example, on Intel's FPGAs, so in that case, I can just modify if they have a code variant for this. Although I think it should work there as well, but if it doesn't, then we can use their template and we can keep the wrapper common, that the wrapper remains the same, and just copy paste the code from Intel's language templates and use that instead. So I'll have to make minimum changes in the code if I use that. So it makes it somewhat platform invariant. That's what I like about it. So it's platform invariant. It's flexible. I can change the size. The other ways that I haven't discussed is that you can also use Xilinx core generator. So here is a Xilinx core generator that has a core for block memory generator. Similarly, if you are using Vivado and IP integrator, then you can add block memory generator IP as well. So here is the block memory generator IP. This is as flexible as the method I have told you. So if you're uh, using Vivado and IP integrated design flow, then it's probably better to use this flow that you use this block memory generator IP. But if you are using RTL flow that you are writing Verilog or VHDL RTL, then it's probably better to use this variant that I have discussed. So that's it.